Good morning, everybody, and a special warm welcome to the radar experts from the Department of Space in the form of National Atmospheric Research Laboratory and ISTRAC ISRO. Today, it is a major milestone as far as the newly established radar facility at University of Calcutta is concerned, because we are having one of the first scientific as well as technical orientation of the students and some of the younger faculties concerned from this region about the opportunities of doing radar research, and of course in course of the entire day we will also learn about the challenges which are involved. In this brief inaugural program, our Honorable Registrar, University of Calcutta, as well as the Dean Faculty of Engineering and Technology, they are supposed to come, but even in their absence, we have our Dean Faculty of Science with us. So we will just go on with the flow of the program, and as and when they are available, they may be requested to kindly speak a few words. So in this program, the day-long program today, as well as the visit to the radar facility at Patra tomorrow, there is expected to be a lot of enthusiastic young students. We have received response from almost like 100 participants. And as in course of my very frequent discussions with the director NARL, that even if we could motivate like 5% to 10% of this number of participants, that will be a good number to begin with in our new endeavor on radar research. So with these few words, I would like to invite Dr. Patra, Director, National Atmospheric Research Laboratory, to kindly come on the dais and give us some his initial thoughts about what is expected or deliverables from this particular program. Thank you, Dr. Patra.
Very good morning to all of you. Thank you, Professor Paul, for making this kind of arrangement. At the outset, I should thank the Vice Chancellor of University of Calcutta for providing permission, giving permission to us to conduct a one-day workshop in collaboration with this particular department. I am thankful to Professor Bishwas, who is the Faculty of Science, Dean Faculty of Science, being present today here, and the faculties of this department and other university departments. Today also we have Professor Nibid Mandal from Jadavpur University, although it is not his field, but he comes from broadly in the earth science. And I'm extremely happy that he has come all the way to basically take the message from this particular school and then propagate this message in Jadavpur University and tell what the kind of opportunities that this kind of field offers to the student. So the purpose of this workshop is, this one-day workshop, is to basically know each other, what is happening in the university system. As you know, we are talking about atmosphere and ionospheric research. In broad sense, it is ionospheric research. Today, I think we are conducting this workshop, if you look at in the background, the backdrop, I think unlike other years, the eastern part of India is receiving less rain. I think you all might have experienced it this year, that this year rain is not much. Most of the rain is happening in the western side. There is a pattern change you can recognize. You imagine that in the next 5 years, if this is going to be the trend, we are going to have problems. Today, we are talking about pollution. I'll show you in the slides that among the metropolitan cities, the Calcutta is not behind. Calcutta is next to Delhi. So things are, deteriorating in terms of pollution, so is the health issues. The pollution in air, the pollution in water, and many other pollutions become a subject. And also the solid waste, I think you might have seen everywhere in the city, solid waste, plastic. So these are going to be of concern when it comes to the atmosphere. We experience the maximum lightning in this area because in the Chotnagpur plateau, just after the Chotnagpur plateau, we have the maximum convection. You have a lot of turbulence, so you can experience when you go by flight. So these are some of the very important things. We have Kal Boishakhi here, we have the cyclone here, and now we are seeing that when we want rain, rain is not coming. It is going to affect the agriculture. Then you might have seen in the last couple of years that in the winter, the temperature is not that low. Temperature is quite high. So there is a pattern change. And you imagine that the temperature is going by 1 or 2 degree. The average temperature is 1, 2 or 3 degree higher. Obviously it is going to have impact. 1 or 2 degree doesn't make sense as such, but it is going to make serious impact. And today all of us are depending so much on the space science, space technology. Lot of technology, including space technology. In a way, actually, it is very important to understand our sphere, not the troposphere or any sphere for that matter, or biosphere, but it is more of a humanosphere. So it's very important to recognize that how this humanosphere can be sustainable, what kind of efforts to be made in terms of pollution, in air, water, understanding the atmosphere, and then make ourselves actually fit for living in the future, because things are going to change. You might have seen recently in the news that in Europe they are experiencing a lot of, the heat. Here we are also facing the heat waves. So these are of very important concern. So that's why, although we are not going to cover everything here, but we are going to talk in general about the atmosphere, ionosphere, the kind of atmospheric processes that we are experiencing, how the ionosphere is going to affect in the satellite-based applications. I see these are some of the topics that I think Calcutta University have been involved. I'm extremely happy that we are standing here when this particular department, the radio science, the radio physics and electronics, which was started none other than by Professor Mitra, has completed 75 years. This country is also celebrating 75 years. It's a coincidence, but it's a great thing that we are sitting in this particular university which is more than 160 years old, and most probably the oldest university in West Bengal. So there are a lot of things that coincide, and most importantly, this particular workshop we have tried to focus that right in your place you have got a state-of-the-art called 53 megahertz mesosphere, stratosphere, troposphere radar, which has come up in Haringhata, already has been established. Now it is time for you to take this opportunity and use this particular sophisticated facility for carrying out research, not only in the atmosphere and ionosphere, but in many techniques. So you are going to get a lot of data. So you can use even machine learning, you can try to develop artificial intelligence in many areas of interest. So it is not that you are going to do the traditional atmospheric science or ionospheric physics, but the kind of technique in the soft domain, in the hard domain that you are going to learn through this particular facility is going to be enormous. And these are all state-of-the-art, sophisticated, latest techniques that are being implemented in this particular facility, which is not very far. Actually, you are very fortunate that you have got such a high powerful radar right in Kolkata. I mean, it's not very far from Kolkata. Usually such high power radars are not allowed in big cities, okay? But somehow it has come. So it's a very, very good, it's a very welcome situation for all of you to really take part in this, learn things and new things. And in this process you will also know that what kind of opportunities and challenges that the present day is offering to us for making our career progress in that direction. So I think the whole idea is to tell you that what actually NARL offers to you in general in terms of carrying out your research. Your research is not actually constrained by the facilities that you have in your department. Actually, National Atmosphere Research Facility is a state-of-the-art observatory and computation facility which is for you, not for us, for you. It's a national facility. So you can actually carry out the top-class research, cutting-edge research using the facility that is built with your money in this country. And that's the message that we want to give. And also we want to give the message that what kind of sophisticated radar technique we are inventing and we are practicing in addition to other things. And the one which is already, in your own place. So the whole idea is to actually talk to the people, the intellectual community in this particular city. That's why it is not in Calcutta University. Calcutta University is organizing this particular workshop for people in and around Kolkata. That's the basic objective, so that we all can actually know each other, our background, our intents, our interest, and whether we can actually find out some common ground on which we can develop collaboration and do high quality research. This is all that. So some of the knowledge that we have generated, we want to actually share with you, and so that we all can grow in our field and produce quality science and do cutting edge research which are of importance for intellectual property and also for the society. So this is the whole objective of this workshop. I won't take more time. I have a long talk, so if I do, I will cut my own time. So thank you very much for attending this. Try to understand. We will be talking a lot of jargon, but try to understand whatever. And if you have doubt, don't hesitate to ask questions, because idea is not to just deliver talks. The talk was very good. We are not looking for that. What we are looking for is that whether we are able to convey something to you, whether you have understood something, whether that excites you, and you come back saying that, yes, I am interested in this, tell me how to go about it. Okay? This is our expectation, nothing more. Okay? Thank you very much.
Thank you, Dr. Patra, for your initial motivating words. It is indeed a great occasion that a very specific scientific community, or those who are interested in this particular area of radar research, we are assembling here in this historic Meghnad Shah Auditorium, which incidentally, or where incidentally, both Madame Curie as well as Pierre Curie had delivered lectures long back. So it is in this place that we are trying to initiate the seeding of a radar research community. It already exists around NARL, centered around NARL, but presently you may be aware that there are 5 radars which are operational in India, starting from NARL, Cochin University of Science and Technology, Calcutta University, Guwahati University, and ARIES in Nainital. In fact, during the initial phase of this radar at Hoingata, we were fortunate enough to be involved in a national level monsoon onset campaign in 2021, where all these 5 radars, they took part, and significant volume of data was generated.
that of course there has to be follow-up action on that related to its proper utilization, analysis and interpretation. So I sincerely hope that Director NARL will also look into that aspect. So let us begin the science part of today's program, and the first talk will be by an overview of the research opportunities at NARL by Dr. A.K. Patra, Director NARL, who needs no introduction to this community interested in radar who have gathered here. Through his talk, this overview, I understand that he will present glimpses of the facilities which are available at NARL, as well as the opportunities for young students from around Kolkata or West Bengal. Because it's a very common trend that we find in most of the research institutes that there are students going from West Bengal. But right now, we have a facility at Horinghata which is world class and is giving very good results at present. So you can also think of that as an option where you can work nearer to your home. So with these few words, I would now request Dr. Patra to deliver his overview.
Okay. So actually you have seen the program. So after this overview talk, we have 4 talks. One on the technique, the radar techniques, and some hardware, important hardware that are important for conducting new experiment. Then we have also how to conduct a radar experiment and carry out the data analysis so that we can get atmospheric parameter, ionospheric parameter, things like that. So you'll get some idea that if such a mammoth facility I have to use, what are the things that I have to really mind, okay? And then we have one talk addressing some of the issues, not all, on the lower atmospheric processes, how radar can be used, and some sophisticated techniques which provide us deeper insight into the processes in the low atmosphere. And one more talk is going to address about the mesosphere, ionosphere, such kind of processes, and what kind of research that we can do, including we'll touch upon some of the applications where you can link it to various applications including society. Then at the end you will also get some details about the radar which has already been established at Horinghata. So you'll get fairly good idea about that what kind of research can be done. So before I start talking, because the main point I want to just deliver is that these talks are going to provide you some inputs, some ideas that what kind of scientific problem we can address, what kind of technical issues, technical things are present which we can work on, and how do we learn new things, okay? And how our research could improve our understanding, and the output, how they can be used for various applications including society, okay? So this is the whole idea, okay? So now I am going to talk about the NARL. So the National Atmospheric Research Research Laboratory, okay. So before that, I already mentioned to you that what is the motivation of this workshop. This is to introduce the R&D activities at NARL and the research opportunities which it offers to you, okay, in terms of doing research. And to initiate discussion, which we will be doing at the end of the, this particular day, that what you have understood from these talks, what kind of opportunities we are providing, and what are the things you have understood, and if you have any doubt how to go about it, how to utilize the facility, what kind of research can be done, okay, what kind of collaboration is possible, whether funding is possible, whether fellowships are available, all such questions you keep in your mind, we will address. So NARL is an autonomous organization, research organization under Department of Space, Government of India. It is located at a place called Gadanki, it's a small village near Tirupati. Tirupati is located in Andhra Pradesh. You may be knowing there is a temple called Balaji Temple, it's a very famous temple. It was established in 1993 as a national MST radar facility. M stands for mesosphere, S for stratosphere, T for troposphere. Okay? These are the three spheres which we know about the atmosphere. And of course, we also do ionospheric research. In 2005, after a lot of expansion took place at NMRF, in addition to the radar which was established, so because the scope has increased, so it was no more called as NMRF, but called as National Atmospheric Research Laboratory. This is the historical background. Why, first of all, a country like this built a radar in 1993, such a huge radar. So we go back in history. This is called Hikamarka Incoherent Scatter Radar. It was established in 1962, around the World War II. And it's a huge antenna, 300 meter by 300 meter, one field you imagine, and filled with 18,432 dipole antenna. It's an array with typically 4 megawatt power to study the ionosphere. Okay? That time it was kind of a, doing discovery, and it has indeed made discovery. So this is the basic purpose. But in 1974, this gentleman, Ron Woodman, who was the director then, he found out generally the incoherent scatter processes are very actually fast. So you send the pulse and get the return and then process. Don't do anything. Because the correlation time from one measurement to another measurement, the process correlation time is so short that you have to make first measurement. Okay? So what he did is, he integrated the pulse returns for several times. I think in this case about 24 or so. Okay? And what he found, the surprising result is that, you see, the power that he's plotting here as a function of height, it is much above the sky noise. If he takes the normal thing, so it will fall somewhere here. It is 316 pulse returns. 316 pulses have gone, and then he has taken return, and he has actually integrated them, and that's the result. So this is how the whole technique, that is, you send the pulse, get the return, very weak and very feeble signal, you keep on integrating, build the signal, and that's how this particular system came up, called the coherent radar technique. That means all the pulse returns, you are adding them in phase. I mean, because the correlation time is so long that if you add, the coherence will be maintained. Coherence means the phase will be maintained. So you build the signal, and that's how this particular thing was born, called MST radar technique. In 1993, of course, in between, couple of radars came in the world. One among them is called the Middle and Upper Atmosphere Radar in Japan, 1988, and this came in 1993 in India. There was a void. Hikamarka is right over the magnetic equator. Japan is a mid-latitude country. In between, actually, there is no radar. So the world community wanted a radar should be placed in a tropical place, and they approached the Indian scientific community because we have a rich heritage of pursuing science. So they told whether India would like to build one. So the scientific community then responded to that positively, and many institutes actually joined together to make one radar as a national facility to cater to the need of the scientists in this country. And there are 6 departments, like Department of Science and Technology, Department of Electronics at that time, DRDO, ISRO, CSIR, all these institutes, they contributed for the building of this facility. Not that they provided the money, but also their participation. That's why it became a national facility. And those who know, or you may know, that what kind of research output has come from this facility and how it has become internationally known. So this is the facility which was started in 1993 formally, but now NARL in the campus, it has a campus of 55 acres. In that, it operates, what is happening? It operates about 50 instruments. They are all, not all, but some of them are here, 50 instruments. Among them, we are currently operating 4 high power radars, operating at 30 megahertz, 53 megahertz, 1.28 gigahertz, and 9.3 gigahertz. We have also 2 very high power lasers, LiDAR experiments, and we have, of course, the digital ionosonde, which some of you may be knowing. Calcutta University also had once, now it is not there. And the balloon, GPS balloon for doing the in situ measurements. So every day we send one balloon and then make the measurement regularly. But when we do campaign observations, we do multiple balloon flights depending upon the type of problem that we are addressing. We have established a high performance computing machine whose capacity is 1.7 petaflop. So you can actually conduct high resolution, high quality simulation experiments, modeling. Now we have actually gone out of Gadanki. Now right in Kolkata we have set up called a Kolkata Camp Observatory that is in New Town. Okay. So this is the facility which is there in the RRSC East campus in New Town. And there is a Hyderabad, in Hyderabad we have set up a camp observatory which is having 25 stations across Hyderabad, and out of these 25 there are 4 core stations where we have lot of sophisticated instrumentation. This particular program is initiated to understand what is the effect of rapid urbanization, like for example Kolkata, Hyderabad, Delhi, Bombay, Chennai, Bangalore. These are the cities which are growing very fast. So because of these fast growing cities, what is happening to our environment, what is happening to the cloud system, what is happening to the rain, what is happening to many things, pollutions, other things. So the whole idea is to study, the effect of rapid urbanization. We have to understand it and project what would happen 10 years down the line or 20 years down the line. What kind of corrections are required for making these cities, mega cities, sustainable in future. This particular program focuses on, you have the deep convection, Kalboishaki. So a lot of these particulate matters from the ground, anything is transported up and it goes up to 15, 16, 17 kilometers. So all these particulate matters, including dust, pollutions, whatever kind of thing, what it is going to do there to the cloud system, to the, it is also kind of aerosol. So what kind of effect it is going to do to the regional climate? So the warming, then the rain, and all these processes, including lightning. So this is the topic of that. Now, in addition to these core observatories, we have also networks. We have a network of GPS receiver across the country, which is done for the space weather research. Okay, the ionosphere and space weather means how the sun is behaving, your coronal mass ejection, and then the solar wind, and all those things are coming. How it is affecting, how they are affecting the Earth ionosphere and things like that, and also the water vapor research. Because today, whatever prediction we do, that is not sufficient, because it is not that Calcutta is going to get rain today. What is more important is that whether rain is going to happen in the airport or not, whether rain is going to happen in Alipur or not, this is the thing, whether it is going to happen in our campus or not, because we are going to conduct a meeting. In that meeting, I want a clear sky. So I want to know, that means very high resolution forecast for this. And the water vapor is so heterogeneous. It is very important to map water vapor, the heterogeneity of water vapor, because ultimately what comes in the form of rain, it is the water vapor. So this is the idea behind it. Then we have also very important thing is the soil moisture measurement is very important for studying the weather. Okay, so soil moisture measurement you can do using the GPS signal. So GPS reflectometry. I think many of you may be knowing GPS is used for, ionospheric research, water vapor research, but GPS can also be used for soil moisture measurement. So these can go, if you have lot of, in our country, actually we have a lot of GPS stations operated by many, many institutes and the national laboratories. All these things, if they are converted into the soil moisture, they can go to the model and improve the model. So we will be benefited from that. We have air glow imager, one at Gadanki, one in Hyderabad, other one is University of Kashmir. So this is the network, and we have a very intense rain gauge network close to Gadanki. This is to validate the satellite products. How much? How many? 40. 40 rain gauge in a small area, 50 kilometer by 50 kilometer area. So this is one satellite footprint we are taking and trying to see that how this rain is distributed in a 50 kilometer by 50 kilometer area, to know the heterogeneity of that. Because ultimately when you want to use the satellite product for anything, you have to keep this in mind, the ground reality. So you know there is a National Clean Air Program. It's a flagship program of Government of India, and we are part of it. And here a lot of this, the pollution related stuff, that the particulate matter 2.5 pm, 2.5 pm to 10, all these measurements are very, very important from health point of view. Okay, so these things we are doing and contributing to this particular program, and this is the network. We are part of it. And today Professor Paul has already mentioned that in the country there are 5 such radars, which are high power radars, starting from Cochin to Nainital. So a large latitudinal belt, and you happen to have one in Haringhat. And so you see the large scale process, the meteorological process, or any process for that matter, we will be able to study the large scale pattern. And since the radars are making measurement continuously in time, you will be able to get the fine scale processes happening at different latitude and different climatic condition. The Cochin climate is different from Gadanki. Calcutta climate is different from Gadanki. So is the case of Nainital. Nainital is located at high altitude. So all those things are there, and the terrain is very different. Here is flat terrain, Gadanki is hilly terrain, Nainital is at higher level. So things like that. And Cochin is on the coast of, the ocean and, Arabian Sea and this thing. So you have very different climatic condition, geophysical condition. So all these things, the understanding of various processes will be known, and also how these processes are feeding to the large scale process, so that the entire, the large scale process is governed by this process. So this is the idea. Now, these are the kind of research, ionosphere and space physics we have been conducting, atmospheric structure and dynamics, cloud and precipitation, aerosol and trace gases, weather and climate modeling. These are the science issues. And parallelly, we are doing equally strongly the radar research, development of varieties of radars, hardware, software, varieties of purposes. And you can see that I have shown you that 4 radars we are operating, but I will show you that what are in the development. You have also the LiDAR research. A large number of LiDAR we have developed for various purposes, okay, to measure aerosol, to measure water vapor, to understand the cloud processes, the polarization and things like that. And also we want to enter into the spaceborne instrumentation, 1 or 2 I will show you. But you see, lot of these instruments we are functioning 24/7, some of them are not 24/7, but based on the scientific requirement, lot of data we are actually generating. So all those data are put into the data center and disseminate the data to the users. Who are users? You are the users. You can take data from the data center and carry out research. So in a nutshell, atmospheric boundary layer, you can see the boundary layer means this is the lowest part where we live, okay, just above the surface. The boundary layer is the process which is actually controlled by the surface property of the earth. And surface property of the earth includes the soil moisture, type of soils and things like that, okay. So this is the kind of instrumentation. Atmospheric boundary layer plays a very important role in the weather, very important role in weather. Atmospheric boundary layer plays a very important role in the air. When we talk about the pollution, if the pollution is not dispersed, they are generated and they are localized there, the density will go up. So boundary layer actually plays a very important role in dispersing the air pollution. For example, you have an atomic power plant here, nuclear power plant here, or you have a thermal power plant here. You just imagine whatever radiation is coming from there, whatever smokes are coming, sulfur dioxide, carbon monoxide, whatever they are coming, they are not going to go there unless there is a wind, unless there is some kind of uplift of the pollution. They are going to be localized, and then the civilization around that place are going to be affected. So it is very important to study the boundary layer and kind of trend and things like that, so that we will know that what kind of dispersion is going to take place, and society is not going to be affected. Aerosol and trace gases are most important thing today when we talk about the climate. But these are not the only things. You have also water vapor, you have other things. But these are very important things because many of those aerosol and trace gases are generated by us, generated by the human beings, which we call the anthropogenic. So we have to have measurement, we have to understand the chemistry among them, and then their lifetime changes. When you say that I am generating carbon monoxide, but carbon monoxide will not stay for long. So the transformation will take place to carbon dioxide, or like many other thing will happen, which will have much longer lifetime. It is going to stay with us for a long time. It is going to affect the climate. Climate is a long-term weather. So these are very important processes, and also the aerosol plays a very important role in the cloud formation, the nucleation of the cloud. Okay, so every aerosol does not do. So only certain type of aerosol can do. Okay, so it is very important to characterize the aerosol in their physical property, their chemical properties, and their affinity to water, things like that. So that's how this is very important to understand that how aerosol is playing a role in the cloud formation, eventually going into the rain. If you have a lot of aerosol, they are not going to do anything. Okay, so a specific aerosol is going to do. So here in this case, I just want to mention here that we have a lot of instrumentation, and we have one particular observatory we call the climate observatory, where all the measurements, you talk about ozone, NOx, carbon monoxide, carbon dioxide, all the other trace gases, okay? Then you have the radiation measurement, direct, diffuse, whatever you call it, different kind of wavelength, everything is done there, okay? So you get actually all measurements, a very comprehensive measurement of the climate parameters, okay? So you'll be able to study long-term data and how things are happening. And Calcutta Observatory, Kolkata Camp Observatory is a mini observatory of this kind. This is cloud and precipitation. We have a large number of instruments here, right from you have SODAR, you have 1.2 gigahertz wind profiler, you have rain gauge, and you have rain radar, you have disdometer, you have towers, everything. So, and then, of course, we have the 9.3 gigahertz, the Doppler weather radar with polarization and Doppler capability. I'll cover that. Weather and climate research, basically it is a high performance computing machine with a capacity of 1.7 petaflop. So you can run very sophisticated simulation, high resolution modeling to understand the physical process, the sorts, the fine scale processes you can actually try to understand because the computation power allows it. And you have also instrumentation along with that. Aerosol structure and dynamics is the core subject with which we started NMRF, called MST radar facility to study the middle atmospheric dynamics. It continues, and we have the MST radar, we have LIDARs, we call LIDAR. Basically what happens when you send the light signal, the wavelength, let us say 532 nanometer we are using. So you get scattering from the air molecules called Rayleigh scattering. Okay, and using those scattering power, you can study the temperature. Okay, you get wind from MST radar. We have also the sodium LiDAR where you can see the sodium density, the variation of sodium density with time, and of course you have other experiments, balloon, and you have radiometer and things like that. Ionosphere, you have, this is a class instrument called Ionosound. This is a HF sweep, HF sounder. We have a dedicated 30 megahertz radar we call Gadanki Ionosphere Radar Interferometry, short called GIRI. It operates at 30 megahertz. It can see the 100-degree sky. Okay, it can map. You can see the image, how things are happening in the sky. You have a long baseline, you can do the interferometry. Interferometry, I think you have studied in the BSc classes, right? Interferometry, so you can do the interferometry, you can resolve the targets. You can do imaging, many things you can do. Of course, you have GPS network. So this is a new area of research that we have introduced in NARL, planetary atmosphere and ionospheric research. Other planets, Venus, Mars, Moon. Moon is not a planet, but it's a heavenly body. So whether Moon has an atmosphere, whether we can probe it, whether it has ionosphere, if the ionosphere is there, how it is formed, and what kind of thickness, what kind of density. So we are going to Moon. So it is very important to understand the Moon atmosphere because our instruments are going to be there. So how they are going to behave. So these are very important. So this is understanding of atmosphere, ionosphere of other planets. So this is the whole idea. Of course, when we do so much, we also generate the forecast we are talking about. So the forecast goes for the rocket launch. Rocket launch is going to happen 15 days down the line. So we want to give the forecast that after 15 days, what will be the weather, whether it is going to rain, what kind of wind will be there, what kind of lightning, or such kind of things are going to happen. These are very important for launch vehicle thing. So this is one thing. And also we provide the high resolution data, for example, wind. Whether the wind has any large value or large CR. CR means the wind varying with height, du by dz. That means the gradient in wind is a function of height. Okay, so because those things are going to provide you the differential momentum onto the body. So this is a satellite body. This is going with U1 and this is going with U2. You just imagine. So the momentum is what? Mass into momentum. This is the mass of this and then U. So U1 is, so there is a differential momentum. So this differential momentum is going to exert differential force, and this differential force could have effect on the satellite, the rocket body. So this is the idea behind it. We have data center, I have talked about it. When you are interested, when you write to us, this particular group is going to give you a link, and through that link you can download data from your home, from your center. So these are the kind of radars that we have developed. The class 1 is here, MST radar developed in 1993, and we have augmented it. I will tell you what this augmentation provides you, the new opportunity. And this is the 30 megahertz GRI, and this is dedicated for ionosphere and space weather research. You have the 1.28 gigahertz wind profiler, which measures continuously round the clock the winds, turbulence, and precipitation and things like that. You have 9.3 gigahertz Doppler weather radar. I think you must be knowing that IMD is operating Doppler weather radar in Calcutta, from where you get some forecast and other things. Okay, and this is of that class, but it has special capability. It measures in two polarization, vertical and horizontal, so you will know about what kind of precipitating system you are addressing, and it has also the Doppler capability, so you measure the velocity of the system. Okay, so this is a large number of LiDAR, which is basically the high power laser, where we measure the Rayleigh scattering, and also we have put a grating there in another LiDAR, completely independent, where we can measure the shift of the signal, and by doing so, we measure the Doppler. And by measuring Doppler, we measure the velocity of the atmosphere from 20 to 50 kilometers, which is not measured by radar. And we are also developing a called differential absorption LiDAR system to measure ozone profile. Ozone, ozone. Ozone is very bad here for the ground, correct? For health, also for the agriculture. But ozone in the stratosphere is very important. That actually stops all the, dangerous radiation which is coming from the sun. Okay. So this kind of thing, and a lot of small instruments, and we have also sodium I talked about. So this is the advanced radar that I am talking about. What we have done, the antenna remain the same. Everything else we have changed. The transmitter system, the control, everything has been changed. Now you see there are small hearts here. Here you have each antenna is fed by one transmitter. We have 1024 antennas, we have 1024 transmitter modules, and each antenna is fed by separate antenna with different phase. So in a way, so you actually can provide the kind of phase you want to give to all the systems, so that you can put the beam anywhere in 360 degree. That's the kind of advantage you will get. So it's a modular. You can use small antenna, small portion, big portion, or you can use different portion of the antenna, and you have 25 receivers, 18 receivers. So you can connect those 18 receivers, and instead of receiving signal at one location, you receive at multiple locations, and then do the correlation, and you know much better information about the target than what you get from one particular receiver. So that's the kind of capability that you can get. And of course, this particular facility, this particular thing has improved the signal condition, because what happened, the transmitter is sitting right close to the antenna, so there is no cable loss. Okay, so this kind of advantage we have got there. And also this particular system provides you the resolution, height resolution. Every 37.5 meter height you can get one data point. Typically in the troposphere up to about 20 or 21 kilometer, you get the wind, turbulence, and all sort of waves and things like that you can study. Okay, then you get in the mesosphere and ionosphere. I'll be covering a little bit in the next talk. So this is the X band 9.372 megahertz, and you might have seen this kind of radome, like a football kind of radome, and antenna is inside. Okay, and this is functioning to study precipitation in and around Gadanki, and we have the rain gauge. You can do the value. You get the reflectivity, you get the Doppler, you get the polarization, but you need to know what this is power, the electrical power, whatever you are getting, correct? How this information is related to the fact on the ground, that is how much rain actually I am receiving on the ground. You need to calibrate. Then you say that if this is the reflectivity, this is the rain. So this is very important to relate. Then the reflectivity can be directly used as a rain parameter, and this is very, very important. So I think I told about the Rayleigh Doppler LiDAR. This is only, it shows that how big is the system, how the laser pulse goes, and then you receive the signal, and then you do the processing, and you get all these parameters. This is a 1.7 petaflop computing system developed by CDAC, and it is a huge cooling system. It offers a lot of opportunity for you people to do simulation. Those who are interested doing atmosphere and ionospheric research, they can always write to us. If you do not have the computation facility, we'll provide you computation facility, and you'll be able to do high quality simulation, modeling, research using our facility. So coming to the technical development, so I told what is actually functional, but the technical developments are continuously going on. The way we are also running many, many new programs. We are talking about, I told you that we are talking about what is the effect of urbanization, correct? This is a true problem today. So Calcutta, 20 years down the line, what is going to happen? Whether every rain is going to flood, whether every year we are going to have a shortage of drinking water. Water is plenty, but drinking water. So these are some of the very important issues, because the water is water, but it is not drinkable because lot of pollution, correct? What kind of pollution? That I won't eat, I won't drink. So it is very important to know the kind of pollution in air, the pollution in water, pollution in soil, pollution in vegetable, everywhere. So it is very, very important to understand to make our humanosphere sustainable for us. So this is a differential absorption LiDAR I was talking about. It goes with two frequencies, two wavelengths. One absorbs, other does not. So there is a differential absorption. More detail when you want, we can provide you the information. But what it provides essentially, it provides you the ozone profile. Okay, it's very, very important, because if I say the ozone is depleting here, what will happen? The UV rays will come here, correct or not? It will burn your skin. You will have a lot of issues, correct? So these are some of the things. So this is the one which I was talking about, the Venus Advanced Radar for topside sounding of subsurface. Venus, you know where it is, Venus, in the planetary system, solar system. Okay, so there is a mission which is already earmarked. It is going to happen sometime very soon. So we are going to have an instrument on board the Venus satellite, Venusian satellite, and we are going to probe the ionosphere of Venus and how the ionosphere of Venus is behaving and changing, and how it is actually experiencing the forcing coming from the sun, that is the solar wind, coronal mass ejection, many, many things, because the magnetic field and other things are going to be different there, right? Earth has a dipole magnetic, very strong magnetic field, which does not allow the solar wind to penetrate deep down, right? So they come, and then just like that, they will go to the polar region. They cannot enter. So like that. So if you talk about Mars, Mars does not have this kind of magnetic field. It has only crustal magnetic field, okay, because of the material, okay. So there, all particles can go down to the surface level. So things are going to be very, very different there. So, and where am I? Okay, and this is I was talking about the lightning. You know the lightning happens. It's a very interesting area, because what happens in the lightning, what we know? We know that we talk about the clouds are charged, right? And two clouds are heavily charged. In between you have the dielectric. It breaks down, current flows. Then when current flows, it is resistive path, so it will generate heat, and also current flows. It will be, this is what you see in terms of light and the electric field. And when the electrons are accelerating in this process from one cloud to another cloud, they actually often exceed the relativistic speed of electron, and they radiate. Any charged particle which accelerates will radiate. Okay, then you have the Cherenkov radiation, you have all sort of spectrum, radio wave spectrum, so you can measure them. And also you can have, if you have high energy, you can have gamma ray. So this is why people talk about terrestrial gamma ray and things like that. So it's very important when you are going to study a particular, so this is the total energy in the system, the cloud system, which is actually getting discharged in the form of lightning. It's like, so this is the potential energy that is stored here, and if I release, it falls. So it is the energy which is there in the cloud, it is getting released in the form of lightning. Okay? But when it is releasing, it is not releasing in one form, it is releasing in the broad spectrum of electromagnetic thing. And of course, you see the thunder. Okay, so you can study more details about that, whether it is possible to actually tell that in advance what kind of lightning is going to happen. Lightning do happen, but what kind of lightning will happen? This lightning, when it breaks down like this, we know this is what we see. But some of the electrons which actually move up to the mesosphere and ionosphere, you know, we call something like sprites, blue jets. You got to imagine there are phenomena, optical phenomena, right? Elves. So these are all actually the electrons with, you know, relativistic speed. They move with very high this thing, so they release the energy, emit light. Okay. So this is a sounder that we have developed. I already told the Venus has a sounder, 1 to 10 megahertz kind of thing. So this is actually can go beyond, and this is the sounder that we have developed in-house, which is called ionosound. Okay, and the softwares are all getting ready parallelly. So this is kind of indigenously developed, which we have so far been purchasing from abroad. Okay, so this is another one I was talking about. I will talk. See, you have the radio experiment, you have the transmitter, you have the antenna, you have the receiver, you can receive in multiple places. If you have the signal strong, you can receive by one antenna. If you have weak signal, you have to receive by multiple antennas so that your sensitivity is more. So this is a setup which is to study the meteors. Meteors actually by naked eye you can see in the early morning hours, right? Have you seen meteors outside? Or Calcutta light does not allow you to see meteors. Okay, so you have to go to some place, Darjeeling or somewhere, and then see the sky in the early morning hours. Before you see the Tiger Hill, you can see the, you know, the meteors are coming. Okay, so those meteors, this radio will go, and this is a plasma trail, right? It's like a metal. Okay, it will hit and comes back. So those signal you can receive, and you can receive by 5 receiver, you can do the interferometry, you can find out the angle of arrival, you can measure the velocity. So you will see about the dynamics. But the meteor trail which is developed when the meteorite enters into the Earth atmosphere, and through friction it generates heat and also the electron density, it gradually expands. So when it expands, you just imagine a trail and the radio wave is penetrating into it. So if the thickness is increasing, so the power will decrease. You got it? So because of that, so you can measure actually the diffusion coefficient of the meteor trail. And this diffusion coefficient is in a way related to the temperature of that particular. Diffusion is a temperature dependent function. Okay? So you can measure actually temperature given the pressure. So if you take pressure from the model, so you put pressure there, you get the diffusion measurement and you get temperature. So you get temperature and wind from that. But you can do much more. I will talk about that in the next talk. So see, this is something very simple thing. See, this is a FM. See, this is FM radio signals are there around Kolkata. Correct? They are radiating. Your radio is there. You are receiving, listening the music. But those signals also you can receive by a simple Yagi antenna, and you will be able to study, because those signals when they are going, they are not only coming to your radio receiver, audio, that is the sound, music and other things. It is also going and hitting the meteor and then coming back. Okay? You will be able to detect those things in a way you can actually study the characteristic of those signals, to study from where they are getting reflected. They are getting reflected from the meteors. So these are very simple experiments you people can try in a college or university. It's very, very simple. This is a long baseline interferometry. This is a 1 kilometer baseline. What it offers you actually, like you have the beam width, for example, 5 degree or 6 degree, correct or not? And when you receive by a long baseline, you will be able to resolve it at much finer scale. So the angular location, each hotspot, how they are moving up, down, east, west, you will be able to monitor. So if you have a turbulent motion, you will be able to see what kind of turbulence is happening. Because all this turbulence theory, I will be talking in the next talk, that whatever theories we talk about Kolmogorov spectrum, I think if some of you know, but in practice, in atmosphere, okay, most of the time, that theory does not work, because that particular theory basically works with isotropic turbulence and for high Reynolds number. You got it? And in atmosphere, most of the time you don't see. It will be low Reynolds number, relatively low Reynolds number, and isotropic. You got it? So most of the time, theory and observation will not agree. That is what is expected, but there is no theory today. Okay, this is the active phased array. We are talking about Doppler weather radar. So it is, I have shown you that football, which is the radome. Inside that you have the disc. And you have a motor system which will rotate like this. Okay, but this is a phased array system which we use for the next talk. Dr. Durga Rao is going to tell the phased array concept. So you have many antennas and you feed the amplitude and phase to each antenna. You can electronically steer the beam, not physically. You don't do like this. Your plate is here and you give only differential phase, and your beam will be going like this. You understand? So this kind of system we are trying to develop. So there are programs. See what happened during this monsoon time. We know that the northern part of India, we have a very dense aerosol clouds. Okay, and this has attracted the international attention and become a political issue. People say that the Indian people, they are creating a lot of pollution. This pollution is going up and then getting accumulated over there. So essentially they say that stop pollution, stop your industries, stop plowing, stop everything and die. You got it? So the question is that whether these pollutions are being created by us or these pollutions are coming from other places by the transport, long range transport. They are coming from some desert, they are coming from the Middle East, they are coming from some other place. But somehow because of the dynamics, they are getting accumulated there. So this is the question that I think needs clarification, because it's a geopolitical problem, geopolitical or what do you say, that kind of problem. See, air quality I have been mentioning, and NARL is paying this thing. So this is the problem. You see, this is the Indo-Gangetic plain, this is the Delhi, I think the most polluted this thing. But you see, Kolkata is also not very far here. You see, can you see in the map here? Calcutta is also, the pollution level is going high. So it's very important to understand that it is not that you are creating all the pollution, but somehow you are actually attracting them and they are sitting over you, okay, or around you. This is something of concern, because these things are driven by large scale process. You know how wind blows? There should be either pressure gradient, there should be a temperature gradient, something must be there, then only things will happen, is not it? Current flows when there is a potential difference, okay? So likewise, so this is very important, driven by large scale process. So it is very important to understand the large scale process and how these large scale processes are actually governing this kind of phenomena, and these phenomena in turn, how it is giving the feedback system to the cloud and precipitation and things like that, and then finally feeding. So it's a loop. I think it's very important to understand. So this is the emission inventory. It is very, very important to know in the country what is the emission inventory. This is for Delhi. So as you know, road, so you have the traffic, you have the vehicles going, so exhaust is coming, so there are pollutions, correct or not? So it is to find out the hot spots where, you know, pollution is more and things like that. So this is very important to know the source, the kind of pollution, the kind of effect it is going to have. So you have to do survey with the hospitals in given season and understand how many people are actually suffering from, you know, the breathing problem and things like that. So these are some of the societal problems that I think we have to get in. Coming to the air pollution, I think I will quickly say Delhi happened to be the winner. Calcutta is not very far. Calcutta is next. So it is very important. It is of concern. We need to. We don't make policy. But if we do scientific study which is trustworthy, okay, it could become the basis for making the policy decision by the government. Okay, this is where we should contribute. We can't change the policy, but we should actually force the management to change the policy. So this is very interesting topic. I think some really pay attention to it. If you have one GPS, see the satellite signal is coming from the through the ionosphere and atmosphere, get delayed, and you measure the delay. That delay you can convert into electron density, total electron content, and also the total water vapor. Okay, but if you have few, let us say 4 or 5 receiver properly spaced, then what you can do? Simultaneously you get the total electron content, or not. In this case, it is the total water vapor, and then you do the tomographic technique, and using the tomography, you will get the profile, not integrated, but you will know the height profile of water vapor. And you are making measurement continuously, because GPS, once you put on when the power is supplied, it will continuously collect data, right? So that means continuously you are getting water vapor profile. This is very, very important to understand the cloud and such kind of process. This is the soil moisture I mentioned to you. It can be done. This is something that we are trying to develop. We have a lot of measurement. We are talking about soil moisture. We are talking about the boundary layer processes, the turbulence, then the aerosols, then all sort of measurements we are doing, winds. So these things we want to put into a microphysical, program, the physics, what physics is happening, and that physics should go into the model to govern the model. Because currently the model that we are running in our machine, most of the physics have been developed by some other people, some mid-latitude. See, America has developed, where it is located, it is in mid-latitude. Japan or Europe, they are all mid-latitude. So coming to the tropical region, equatorial region, we have different processes. We have convection, we have cyclone, we have many, many things, right? So the physics is also going to be different, and not only that, the physics is going to be different from one location to another location, because the terrain is different, the climate is different. So it is very important to understand the microphysical schemes, and those microphysical schemes should go into the model to truly represent the physics in the model. So these are some exotic things we are doing. We have a high power radar, I have shown you, 1024 antenna, etc., etc. We have power about 1 megawatt. If you send the signal, you can get echoes from the moon. So you can actually do the imaging of the moon surface. It is doable, okay? You can see some raw image have been developed. See, you have also a lot of debris in the sky, the satellites and the debris, okay? When the radio wave is going, definitely they are hitting and then they are coming back. Some of those things we do not know, we don't address them, but they are buried in our data, okay? They are unwanted signal. Our data is getting contaminated. It is very important to know what are unwanted signal, which is not atmospheric parameter. So we have to come up with some kind of, that's what I was telling, artificial intelligence, machine learning, deep learning you can adopt and identify which is not atmospheric parameter. Those signals have to be removed in an effort to get the high quality, reliable atmospheric parameter. But lot of learning, lot of mathematics, lot of intelligence we have to develop, and that is where you can sharpen your brain. This is something coming from the International Space Station, you know, which is about 250, 300 kilometer altitude. So you have also the other small satellites which you can monitor by this system. So if we are able to monitor, the Haringhata also can monitor. I am almost, I've taken too much time. So now before you, I just want to propose that you have plenty of experimental system, state of the art in this country. You remember that most of this kind of instrumentations were there in the West, not in our country. But today we are fortunate that we have many of them with us. May not be with you, but somewhere. But good part of it is that they are operational as facility, so you can use them. This is the great part about it. And here you can actually think about some experiment, you can think about some investigation, you can come up with a proposal that this is what I want to do, this much data I want, or I want to conduct this experiment and things like that. So your experiment will be conducted, your data will be given, people will be there to help you, guide you how to analyze the process. You will get some glimpse of it today itself, and you will be able to carry out high quality research despite the fact that you have limitation at your home. Okay, and so you can, any extraordinary, any idea, just an idea, you can just write one page, short one paragraph, this is what I want to do. This is what we call the exploratory experiment. Nothing to write a big proposal or anything like that, just shoot an informal mail that this is what I want to do, is it possible? Okay, you will get an answer that yes, this is the thing, can we have a discussion or something like that, and then we can fine tune also. You may be having some ignorance about some of the facts, so we can fine tune that one, you can conduct experiment, you can analyze data, you can do your research. And so you can conduct experiment, you can use the existing data of last 30 years, and you can do also research using the high performance computing machine. Only thing is that the topic should be related to atmosphere, ionosphere, space research, which is of our interest. And you can also do collaboration. See, for example, you do not know, but we can develop collaboration to benefit your research. You got it? Whatever we can do, we will do, but it is your program. We only come and help you in addressing that issue. Okay? So we have newsletter. We can, if you give your email, we will circulate that, the new opportunity. I think I might have missed many, but during the interaction session I will cover. Thank you very much. And you think about it that these are the facilities, they are available to you. There are something which are called national facilities, and those facilities you can spontaneously use. There are some instruments which are very specific and all that. It is very important to discuss with those scientists who are doing that, because details about that experiment, they are only handling. So you have to do collaboration. I mean, I am telling you straightforward that certain things you can just do like this without botheration. Certain things you need certain discussion, collaboration, handshaking and things like that. Those things need to be developed, through correspondence, interaction, things like that. But question is that everything is possible, and you need to understand that lot of opportunities, lot of facilities are coming up. These are, and many of them are actually addressing the challenging issues of today, and we must participate, sharpen our brain, do some quality research and make progress in our career. Correct? Thank you.